Hello, I'm Yasha from Bar-Ilan University, Israel. You are watching a series of lectures on philosophy and methodology of science. We are going through the experiment low temperature measurement of superconductivity. This lecture is about numerical modeling. In the previous lectures, we found that our measurements do not correspond to the expectation. So we are about to introduce a new method which will describe, approve, or not the findings from the experiment itself. We have discovered that the metallic material that surrounds the superconducting filaments might affect the energy loss in the wire, because we saw that for mono material there was a strong dependency on DC current, which we didn't see in the titanium sheath. So we have to redefine our research questions according to those new findings. The research question will be: in what way energy losses in wires made of magnesium diborate depend on frequency, current amplitude, temperature, and metallic sheath surrounding the superconducting filaments. To answer these questions, we need to introduce additional method, the numerical modeling. Let's understand what is numerical modeling. A computer model that is designed to simulate and reproduce the mechanism of a particular system. Mathematical representation of all the physics and interaction of the experiment will allow us to change any independent variables as we wish, and to get the desired results, and to observe the phenomenon which are not measurable in the real experiment. The finite element method is the method we're going to use. You can check this in the bibliography. For example, a human leg was modeled with this technique. As input parameters, the bone properties, the geometry, the mechanical properties, how it will contract under the stress, and breaking points, and so on, are introduced to the model. And this allows us to see the distribution of forces and stresses in the bones, and the fracture, if it happens, and where it would happen according to the model. Another example is from environmental science, is the electrical resistivity tomography of El Capitan rock in USA. It's a very useful technique in geoscience and aerospace, engineering, and automotive industries, medical research, and fundamental science. This technique can help us to optimize our experiment, to get the predictions of the result of our experiment, and probably the most important is to see locally what would happen in the areas where we cannot see or measure it because of the technological obstacles, like galaxy research, nuclear blast, or so on, where experiment is very impossible to conduct, or not welcome to conduct. Another example, a bit closer to our research, is the stresses in the MRI magnet, von Mises stress. Especially in engineering and applied physics, before you create any device which can cost a lot of money, you have to make optimizations and to be sure that your device will work as expected. So this tool is used by many companies and researchers worldwide. And for our research, we're about to model our MGB2 wire, the first one with the Monel matrix. So our input parameters are electrical resistivity at 10K and magnetic permeability, mu, as a function of magnetic field. We can see that permeability decreases with the magnetic field. At this point is called magnetic saturation. At this point, the magnetic material performs as non-magnetic one, more or less. It loses its ferromagnetic behavior. That's an important point. You will see it later, in a minute. For this domain, which is a superconductor, we define the magnetic permeability is 1, and of course we put the current density at specific temperature of 10K and a very low magnetic field. It's a self field. The next step of the finite element modeling is the meshing. This numerical technique requires the division of the whole model into small sections. You see this mesh, this net. On every intersection for every node, this Maxwell equation is solved, involving the parameters we defined earlier. So the result, it takes into account the specific local parameters of the material involved. So let's see what we get. We put AC current with no DC current at 100 Hertz, and this is the result. First of all, the color code, the blue and red and green, is the current density in the superconductor. So you can see during the cycle, during the AC cycle, it changes from +2 to -2. These are arbitrary units. The grayscale is the magnetic field produced by this current. So we can see by this arrow the direction changes every time the current changes its direction, which is expected. But what we see that the whole inner area is totally screened from magnetic field by the superconductor, and all the change happens on the outer shell of the superconducting wire. Since this material is electrically conductive, and change in magnetic field produces electrical field in it, that means there will be currents flowing in the mono material, and of course currents in the resistive material causes losses. But when we introduce some DC bias, you see the same AC current flows around the 40 amps of DC, and the result is quite different. First of all, we have overall much more current in it, so more filaments are occupied with the superconducting current, and the less area is screened by the superconductor. But the interesting part is that the change in magnetic field is way lower than in the previous case. You almost cannot see the movement of the arrows. That means the change in magnetic flux is lower, and this produces much less eddy currents in the monomaterial. So this explains why we saw the reduction in energy losses when we put additional DC current. This is also explained that the main source of the energy loss is actually a monomatrix and not a superconductor itself. So by numerical modeling, we could explain our results that our measurements were actually right, and this makes sense that due to magnetic saturation, the change in magnetic flux in the mono matrix is less, and less energy loss occurs. Because of this mechanism is also responsible for the dependency on the frequency, because on higher frequency, the higher the magnetic change rate, more eddy currents induced in the metallic material. That is why we saw the strong dependency on frequency. Of course, we have performed many simulations like that. We played with the different properties of material, magnetic, electrical, and so on. And we saw that for non-magnetic material, as a titanium, we didn't see any change by introduction of DC current. So this technique allows us to approve our measurement and to understand more deeper the mechanism responsible for the energy loss in the superconductor. The applicational benefits of this are that we cannot use magnetic materials for applications where alternating current occurs, only for DC applications, and some additional optimization is required to achieve minimum energy loss for high frequency power applications. So numerical modeling is a very, very powerful tool to research where experiment is impossible or very difficult to conduct. A combination of experiment and modeling can provide us a more deeper understanding of the research topic and provide a better results than every method by itself. In many complex problems, computer simulation can provide a prediction of the experiment result and help to optimize the experiment procedure. For a very complex experiment, it's almost mandatory to use modeling to have better predictions and to build, to design your experiment better and to eliminate many problems by conducting this virtual experiment. And in addition, a number of physical phenomena can be combined into one model, including their interrelationships. It's called multiphysics. For example, beside magnetic and electrical properties, we can add mechanical properties because, for example, temperature, contraction, and expansion for different materials is different. A stress can also affect the properties of the materials. These energy losses produce some heat, so we can see where the heat is generated and how it's distributed with time, and changing the parameters, and many, many more. Almost every physical phenomena that can be described in equation can be added to the model, and all the interrelationships are taken into account. Of course, it will cost you the computational time and effort to make this model work. Okay, let's summarize the experiment. First, we identified the problem, the superconductivity in our case. We had the literature review, they formulate the hypothesis. We have designed and construct the whole experiment. After that, we conducted the experiment. We measured the energy losses, and we saw the data, and we have discovered some new findings during the measurements. So we had to come back to the point of hypothesis formulation to refine the research question, and we added additional method, the numerical modeling, to have a deeper understanding of the local phenomenon, local processes happen in a superconducting wire. Then we conduct additional experiments. We approved that our measurements were definitely right, and there was no mistake. And we finalized the experiment and the conclusions. This structure is uniform for almost every experimental research. These steps are crucial for every experiment you conduct. It doesn't matter which exact science area you come from. Remember to formulate your hypothesis precisely and to formulate the research question so you will be able to answer it properly. Always compare your results, your finding with the literature, with other research group. So together you can provide a more wide scientific knowledge of the area. I wish you a good luck with your experiments and your research. Thank you for watching.